to everyone for being here. Yes, I think the screen is visible. Since this is the second part of the talk, but I would prefer I will quickly go through what we have done the previous lecture so that most of you are up to date with the results. So we were trying to study threefolds over any field of this form. Kxyzt modulo this equation x to the power my minus fxzt, where, well, m I have written here, m is strictly greater than 1. Well, some of the results will also include the case when m is equal to 1. And what we were trying to do, we were trying to investigate or find out conditions, equivalent conditions, for which on this fxzt such that A is stably a polynomial ring, and maybe A itself is also a polynomial ring, and this equation defines a variable in kxyz. And for that, we needed some definitions. Well, so just to recapitulate, if you take a polynomial in two variables over a field, that thing will be called to be a non-trivial line. Well, what is a line? Line is some polynomial. If you go modulo that polynomial, the quotient is isomorphic to k1. So kzt mod f isomorphic to k1 says that f is a line. But this f need not be a variable. So we cannot be able to find, suppose there, so there might be some f for which there does not exist any g such that kzt is equal to kfg. Such examples do exist in positive characteristic, but never in characteristic 0. So, and this was the main problem which we were interested in, to investigate the Zariski cancellation problem for polynomial rings, which asks that if you have an affine algebra over a field such that it is stably a polynomial ring in n+1 variables, then is it isomorphic to a polynomial algebra over k in n variables? Well, some cases were already known. We said those cases, and this example, what we are dealing with now, deals with the case n equal to 3, which was open for long. So I am not going through these results again. And this also we can exclude for now. So let's come to this. So what Neena Gupta proved, that over any field K of arbitrary characteristic, one has this let's forget the previous result, but look at this, that if you take a polynomial like this, x to the power fw minus bxyz, where m is strictly greater than 1, f of yz is, if you evaluate this polynomial at x equals to 0, b of 0 yz, and capital F is, then the following are equivalent. That this, if f, this small f is a variable in kyz, then this A is a polynomial ring in 3 variables. So there is something to deal with a polynomial being a line as well as being a variable or not, which creates the obstruction whether this quotient A is a polynomial ring in 3 variables or not. And then we came to something which was a little bit generalization of local nilpotent derivations over a ring called as exponential maps. And these were the main assumptions, like over an affine variety, these are the algebraic actions of K plus. And there were ring of phi invariants of an exponential map, and some examples were given. And they can be related to something called as locally finite iterative height. I will not go into those details now. And some properties of exponential maps, because we need to remember this if we want to go through the proofs, like local nilpotent derivations, you can compare them, that the ring of invariants of an exponential map is like the kernel of a local nilpotent derivation. So if it is a non-trivial exponential map, a phi is factorially closed, is also algebraically closed. Transcendence degree is 1 less than the transcendence degree of A. There is an element like a local slice or a minimum phi degree. So that if you invert this element, it becomes a polynomial ring over that localization. And if there is a one-dimensional ring, transcendence degree A over K is 1, then A is K bar 1, where K bar is the algebraic closure of K in A. It's not the total algebraic closure of K, only the algebraic closure of K in A, and Fi is K bar. And also you can extend exponential maps to over rings through localizations. If you take a multiplicatively closed set, then phi extends to a non-trivial exponential map S inverse phi on S inverse A, with the ring of invariance as S inverse A phi. Then we defined the Duxon invariant. Duxon invariant for local and nilpotent derivations is the algebra generated by kernels of all non-trivial local and nilpotent derivations. So similarly, Duxon invariant of a ring can be defined also as K of the algebra generated over K by all the elements in the ring of invariance of non-trivial exponential maps. For a polynomial ring, it's quite easy to see that the Duxon invariant is the whole ring, because you have partial derivatives which can be written in terms of exponential maps, and the proof is very obvious. So this is, one can say, a necessary condition for an affine domain A to be a polynomial. So if this condition is violated, we can discard A at that very moment, that it can never be a polynomial. But obviously, decay A equal to A does not imply that A is a polynomial. It is a necessary condition. So this is what I meant by this remark, that if A is an affine K algebra such that transcendence degree A is strictly greater than 1, if the Duxon invariant is properly contained in A, obviously it can't be more than A. If it is properly contained in A, then A is not a polynomial. So this is the main theorem. Maybe this theorem I will again state, maybe the equivalent conditions might be shuffled. So let's go through these conditions one by one. Let A is kxyzt modulo x to the power my minus fxzt, where m is greater than 1. I will always denote capital G to be that equation, x to the power my minus fxzt. Small f will always denote f of 0zt. And small letters will denote the images of the variables. Then the following are equivalent. A is isomorphic to a polynomial ring in 3 variables. It is x is among the x is one of the variables, so it is a polynomial ring over x also. Fzt is a variable in kzt. G is another variable, so you can see this x to the power my minus fxzt. G is a variable in kxyzt along with x. So G and x form a part of a coordinate system also in kxyz. A is stably a polynomial ring, and the Duxon invariant is the whole ring. A is an A2 fibration over kx, and Duxon invariant is the whole ring again. Kzt mod f is k1, that is f is a line, and the Duxon invariant is the whole ring. Duxon invariant is the whole ring. K1, the first K group, K1 of A is K star, and A over K is geometrically factorial. Duxon invariant is the whole ring. A mod xa is K star. Let me recall what was A mod xa. A mod xa will be kzt mod small f 1. So A mod xa is always a polynomial ring over kzt mod small f. Now if kzt mod small f, like for example f is a line, if kzt mod small f is k1, then obviously A mod xa becomes k2. So A mod xa star is k star is something one should expect, if one of these conditions is satisfied, obviously. And how the role of this first K group comes, well, I will state some results of K theory, maybe without proofs, because they are beyond my scope and also the scope of this lecture. But just to tell you, if it is a polynomial ring over a field, the first K1 is always K star. K1 of a polynomial ring over a field is always K star. So it is like another necessary condition which you must have to show something is a polynomial. So the consequences we discussed also, how we can also study some non-triviality of the Russell chorus threefold will follow from this theorem. Okay, there's something in the chat, I think. Okay, geometrically factorial means, suppose A is a affine K domain. If you take if you tensor it with the algebraic closure of that field, so A tensor K bar over K, that is still a UFD. So A is a UFD and A tensor K bar is also a UFD. So that means geometric factor. So every UFD, if you tensor with the algebraic closure, need not remain a UFD. So that property is preserved.
But let me ask, so in one direction, if you have some if you have an algebra over non-closed field, it can be non-factorial, but after tensoring with algebraic closure, it becomes factorial. This is possible.
No. I'm not saying that. I'm saying for geometric fact, it has to be factorial at first. Okay. But then when you tensor it with some extension of that field, it still remains factorial.
So the requirement is that the original algebra over non-closed
also is a factorial. So first of all, geometric factorial will mean the algebra is a factorial. First of all. And if you keep tensor with something, then it also, that property is preserved, basically. Okay, so let's keep this. Okay, so this was another thing which we discussed, like how non-trivial lines come into play, but they will come up in our discussion, so let's not worry. So since it was requested that I don't go through lemma 1, lemma 2 like that, so I will skip these slides and maybe we can come back if we have time. So this is another thing which I did almost at the end, but I need to specify. If you have a Z filtration on a domain, it is called proper if you have this condition 4, that so that the GR becomes, the associated graded ring becomes a domain. That if you take something from AN minus 1 and AM minus 1, that will not lie in AN plus M. It will still lie in AN plus M. And if you have a finite generating set, it is called as admissible. Well, for finitely generated K algebras, we will have the situation for most of the cases. But why is it important? If it is important because we have something called as homogeneous exponential maps. So this is the theorem, maybe I should say, which is important. This theorem DHM proved by Duxon, Hadas, and Makar-Limonov, that if A is an affine domain over a field with an admissible proper Z filtration, and GRA is the induced graded domain, if you have a non-trivial exponential map on A, then it goes to a non-trivial homogeneous exponential map phi bar on GRA, such that under that map rho, which goes from A to GRA, rho of A phi is contained in the ring of invariants of phi. That is the thing we might require in one of the proofs. This is again, we skipped, and okay, so let me go to okay, I will state this is one result we should also remember. Not maybe the proof we can skip for now. For this threefold, where M you can take even greater or equal to 1, the K of XZT is always contained in the Duxon invariant, and the Makar-Limonov invariant is contained in Kx. Well, how I've not written explicitly how to define the Makar-Limonov invariant. It is as usual, the intersection of the ring of invariants of all non-trivial exponential maps. And actually, one can show that it is an equality if M is strictly more than 1. For M equal to 1, there is an issue. The proof is not difficult, but probably we can come to that. Okay. So this is one proposition which I want to state, and maybe proof also to be we can do later. This is important, our key proposition in the proof. So I have taken M greater or strictly more than 1 or M greater or equal to 2. Suppose dKA is A. Now, if you have this and set f of 0 zt as fzt, then there exists z1 and t1, that is a coordinate system in kzt, such that kzt is kz1 t1, that means z1 t1 is a coordinate, and f you can write sort of a linear term as a linear polynomial terms of t, a0 z1 plus a1 z1. Moreover, here it is another interesting result. If f turns out to be a line, then it has to be a variable. So remember, what was the hypothesis here? The hypothesis is only dKA is A. So for example, if A is a polynomial ring, that hypothesis is satisfied. So in that case, you do not have chance of this f to be a non-trivial line. So this is one result which we have to remember and use. Okay, proof I skip for now. And this is another theorem. So let K be a field of characteristic P, positive. Now we will see how this proof of this theorem will follow soon. And fzt is in kzt such that kzt mod f is k1, but kzt is not kf1. Immediately I can say from what we have proved in proposition 7 that A is not isomorphic to K3. Because see, you have a line which is not a variable. That cannot be true. That means decay of A cannot be the whole ring. Because if decay of A was the whole ring, this F had to be a variable. So it directly shows that A is not isomorphic to K3. In fact, it gives a proof of the Zariski cancellation problem. This example, that is an example which says that the Zariski's conjecture is false in n equal to 3. Only thing we have to show that A is stably a polynomial. Apart from that, that A is not isomorphic to K3 is already established by proposition 7. Okay. Proof follows from proposition 7 as dk is not equal to. Now, why is it is stably polynomial? Well, one can always refer to results of the structure of A2 fibrations over Kx by Asanuma, because you remember A is an A2 fibration over Kx. Well, to recall what is an A2 fibration, it is a finitely generated flat. An A2 fibration over a certain ring R is a finitely generated flat R algebra, such that if you tensor with the Kp, for Kp is Rp mod PRP. PRP is a prime ideal of R. So if you tensor over R with Kp, A tensor Kp will be a polynomial ring over Kp. Kp is a field. Kp is the residue field of the local ring Rp. So A tensor Kp is Kp2. So polynomial algebras are A2AN fibrations. So if it is a polynomial algebra in two variables over a ring, it is an A2 fibration over it. But not every A2 fibration is a polynomial algebra. So by a structured theorem of Asanuma, you can always say that AL is Kx L plus 2 for some L greater or equals to 0. Well, now what is the value of this L? We can't be sure. We can't say that L has to be 1, L has to be 2, L has to be 3. Well, there may be bounds on that. But so A is stably a polynomial algebra that is somewhere settled already by Asanuma. But what Neena Gupta has improved Asanuma's result, she proved that A1 is actually K4. So you can, so it will be not L plus 2, it will be, I think, L plus 3. Or if I have to, no, it is correct, it is correct. X is always there. So what Neena Gupta has proved that A1 is K4 and X is one of the variables. You can take it is over isomorphic over Kx to Kx3. Well, I will give a proof also of this. So as a consequence of both these theorems, we can say that Zariski's cancellation conjecture does not hold for any threefold defined by this form, where you need two things. You need M to be strictly greater than 1 and this F to be a non-trivial. Then A1 will be K4 and A will not be isomorphic. So before we go to the proof of the main theorem, I will again list the results in one page, try to list the results in one page so that we will use this theorem, but maybe later I will come back to this if you need, that if this is a result by Russell and Sathe, and it was written in this format by Datta and Das, let R contained in D be a domain such that D is a finitely generated R algebra. Suppose you have a prime element pi, which such that pi remains prime in D. So if you go above, if you take pi above, pi still does not break up, it remains prime. If you invert pi, it is upper D1 by pi is R1 by pi 1. Pi D intersection R is pi R. This means that R mod pi R is, there is an injective map from R mod pi R to D mod pi D. And R mod pi R is algebraically closed in D mod pi D. If you have these conditions, then D is a polynomial algebra. And for this threefold, we have these results which we will need, that A is a UFD if and only if the element X is a prime or a unity. If and only if FZT is either irreducible in KZT or FZT is a unit. This is actually lemma 1. A is an A2 fibration over Kx if and only if FZT is a line in KZT. This was formulation of lemma 2. And so these two results will, the first two results which I stated for A will not require your M to be strictly more than 1. They are true even for M greater or equal to 1. Now that this result, including proposition 7, this proposition 7 needs M strictly greater than 1. Suppose dk is a, then there exists z1 and t1 such that kzt is kz1 t1, fzt is linear in t1, and if f happens to be a line, f has to be a vector. And kxzt, this again requires m strictly greater than 1, that kxzt is contained in dk. So maybe I wait for 1 or 2 seconds so that you may have a look at these results, and then we will continue. Okay. Now, some results from K theory which we need. Well, by K theory here, when I say K0, K1, and K2, they are the usual Milnor K groups. And through plus construction, Quillen later extended, gave the definition of higher K groups for rings. So the most of the results I will quote are due to Quillen, and I'm following a textbook of V. Srinivasan algebraic K theory for explicit proofs and statements of these results. So what we will let R be a regular ring, U is an indeterminate. So R1 is a polynomial. This inclusion map induces an isomorphism between KIR and KIRU for each I. And there is a exact sequence from KIRU to KIRU U inverse to KI minus 1 R to 0. And this is a split exact sequence. So basically, KI RU U inverse is a direct sum of KI minus 1R and KIR. So how will we use this? You see, if something maybe is a polynomial algebra or something, by the first result, you can reduce the KI of that bigger thing to the KI of the smaller thing. So suppose if A is a polynomial, A is some Kn. So what is KI of Kn? KI of Kn will be KI of K. KI of K is what? That is K star. KI of maybe K1, I'm speaking maybe for I equal to 1. K1 of a field is K star. And maybe we can use these, the second thing, for cases like where we do AX, X inverse and stuff like that. Well, they will be clear. This is another important. Let R be a regular ring and X is a non-zero divisor such that R mod X is also a regular ring. And you take the inclusion map R to X inverse, then there is a long exact sequence of K groups. KIR mod X to KIR to J star. J star is induced by J to KIR X inverse, then the connecting homomorphism delta to KI minus 1 R mod X. And if there is a flat ring homomorphism phi from R to S such that both S is regular as well as the image of X, U, S mod U is regular. Like initially we had R regular, R mod X regular, and X is a non-zero divisor. The ring homomorphism is flat. So it will go to U is also remain to be a non-zero divisor. So then we have this commutative diagram. Like you have the first thing from the, like for R and the next thing from S, and there are vertical arrows. Well, we will not need all these results in full generality. We will only need for K1 and K2 at most. So not beyond that. And this is another elementary result also, which follows since K1R can be written as R star direct sum SK1. So if there is an injective ring homomorphism, then obviously the map, there is a map induced from phi star from K1R to K1B. It maps R star injectively into the subgroup B star of K1. Well, I know these results are not easy to remember, but let's see how much we can do. So this is how in the format of the main theorem I will prove. As you can see, the notations are as usual. So KXYZ is KXG2, KXYZT is KG3, A is KX2, A is K3. The usual AL is KL plus 3, A is an A2 fibration over KX and DK is A. And there are two conditions with geometric factoriality. One is K1A is K star, another is A mod X star is K star. KZT mod, KZT is F is a variable, and KZT mod F is K1 and DK is A. So let's start. So 1, 2, 4, and 5. So I am keeping this slide. So let's look at the implications. 1 easily implies 2. 2 implies 4. Why 2 implies 4? Because A is what? A is kxyzt mod g. 4 implies 5. That is obvious. So these implications are easy. 1, 2, 4, and 5. Let's look at 1, 3, and 6. So 1 and 3, that is fine, because again, A is kxyzt mod g. So 1, 3. Now 3 and 6. 3 is what? A is kx2. Obviously, if it is a polynomial algebra over kx, A is an A2 fibration over kx. A is a polynomial ring over k. So decay of A is A. So these implications are obvious. So what we need to show? We need to show these things. That for the first set of implications, 1, 2, 4, 5, we want to extend it to 5, 7, 8, 9, and 1. And the other part I will see. So one by one, each time I will go back to the main theorem, so let we have an idea of what we are proving. So 5 implies 7. So let's look at the main theorem. So 5 implies 7 means A is stably polynomial over K and dk is A. And 7 means A is geometrically factorial over A, dk is A, and K1A is K star. So dk is A is one, something is common. See, if A is obviously stably a polynomial algebra, so A itself is a UFD because it is a retract of AL and KL is that thing. Geometric factoriality is not difficult. The main thing is to prove K1A is K star. Because A, so let's see how to write that. This is by the first theorem of K theory. We recall if we had Ki of R was isomorphic to Ki of Ru for each I. We only need K1 here. So K1 of A is same as K1 of AL. So if I go back here, look at 5. K1 of A is same as K1 of AL. Now K1 of AL is K1 of KL plus 3. What is K1 of KL plus 3? That is K1 of K, which is K star. So that condition is easy to show. 7 implies 8. Well, 7 implies 8 is a bit long. 7 implies 8. Only we have to remember these two all these two, geometric factoriality and Duxer invariant, are same. That if K1A is K star, we have to show A mod X star is K star. So we will assume K1A K star and we want to reduce this. So just keep that in mind. So dk is A. Now what proposition 7 said? As soon as you have dk is A, you can have a set of coordinate system z1 t1 of kzt such that you can write f as a linear polynomial in t in kzt. So we rename them as z and t again. So we can assume that fzt is a0z plus a1z. Now there are two cases. It might be just a polynomial in z, or it might involve t. So case 1, a1z is 0. Now, if a1z is 0, fzt becomes just a0z, a polynomial z. Now, remember, A is geometrically factorial. So, if k bar is an algebraic closure of K, A tensor k bar is a UFD. Now, I use my lemma 1, which says if A is a UFD, fzt is either irreducible or a unit. Now, what is fzt here? Fzt is just a0z. So, I have written a0z is either irreducible in k bar zt, or a0z is in k bar star. Now, if a0z is in k bar star, let's look at the equation. A is isomorphic to, then A will be isomorphic to, because this is fzt is a unit now. So it will be isomorphic to x inverse zt. And K1 of a ring always contains its group of units as a subgroup. For any ring, K1 of R will have R star as a subgroup of it. So you see this ring A, if it is isomorphic to Kx inverse zt, it has non-trivial units. X is a unit there. So K1A can never be K star. It has to be something more than K star, which is a contradiction to our assumption. So A0Z cannot be a unit. So what is the only other possibility? A0Z is irreducible. Now, if A0Z is irreducible, it has to be linear in Z, because it is a polynomial in Z over an algebraically reduced field. So f is a variable in k bar zt, or most probably you can say a naught z is linear in z. That is what we need. And a mod x is what? Here it got clipped a little bit, kzt mod f, where f is a linear polynomial in z. What is a, if you quotient by a linear polynomial, you will always have k1. So a mod x is kzt mod f1, which is already there. Now kzt mod f we have obtained is k1, so it is k2. So a mod x star is k star. Actually, we have proved a little bit more here. We have proved that f is also a variable in k bar zt, which might be needed in some other implications later. If we could have proved that f is just a line, it would have been fine. Anyways, so this settles the case where a1z is 0. Now, next case, what happens if a1z is non-zero? So there t comes into the picture. It's not just a polynomial in z. So there is no chance of f now to be a unit in kzt. So f is irreducible in kzt. So if you take the coefficients a0, 0, and a1, the GCD of the coefficients is 1, and the GCD is over kz, which is a PID. So you can write them as a linear combination. And to some commutative algebra and ring isomorphisms, you can show that a mod x is isomorphic to kz 1 by zy, polynomial ring in one variable over kz 1 by z. Also, you have a x inverse kxx inverse 2. This was already there. Now, since both a mod x and ax x inverse are regular, so is a. This can be proved by the definition of the local property of a regular ring. For a regular ring, what is a necessary and sufficient condition? If you localize at each prime ideal, it has to be a regular local ring. Now, a prime ideal of this ring A will either have x or it will not contain in x. So it will be either, you can relate it to a prime ideal of A mod x or a prime ideal of x inverse. And both of them are regular rings. So the localizations will be regular local rings. And so it follows that A is a regular ring. So to apply the theorems on K theory, we need the rings to be regular. So this only requires we show that the ring is regular. Now we use the long exact sequence. So for I equals to 2, maybe, yes. K2 x inverse, there is a connecting homomorphism which goes to K1 of A mod x, K1 of A, K1 of AX inverse, and it goes on. But this map is J star. J star is induced by the inclusion. Remember, what was our hypothesis? K1A is K star. Now, if eta is the inclusion of K in A, and you compose this eta with J, so what you have? You have a totally an injective map from K to A to AX inverse. So J compose eta is an injective map from K to AX inverse. So by that lemma, the elementary lemma, the induced map J star compose eta star will map the units of K, that is K star, injectively into the units of this ring, A mod X inverse star. Now, what is K1A? K1A is K star, and K star is eta star of K1K. K1 is eta star of K1K. So J star maps K1A. This J star actually maps K1A injectively into K1 of AX. So we know, now we have a shorter sequence now. This J star is injecting what we have obtained. So we have this exact sequence. K2 AX inverse delta to K1 A mod X to 0. Since J star was injected. Remember. Now, AXX inverse is KXX inverse 2. So again, you can use the equivalence theorem for KIs, that over a regular ring, KI of RU is KI of R, and KI of RU inverse is KI minus 1R and stuff like that. So think K2 of AXX inverse is KXX inverse 2. So K2 of KXX inverse will be same as K2 of AX inverse. Now, we also have this split exact sequence from that theorem also, that K2 of Kx goes to K2 of KXX inverse to K1, K2, 0. A is a torsion-free module over Kx. Why? A is an integral domain containing Kx. So it is a torsion-free module over a PID, hence free module over a PID, and hence also a flat module over a PID. So we can use that commutative diagram. So you see from the top row we have from the second line, K2 Kxx inverse delta K1 K2 0. This map is surjective. I don't need what is the kernel of this map. And the bottom row I've taken from the first exact sequence written in this page. K2 Ax inverse delta K1 A mod x to 0. And we know that the top left and the bottom left are isomorphic. This diagram is commutative. So what you have by diagram chasing, you can say this map phi star will be surjective. And by lemma 3, we already know. So let's look at phi star. Phi star is a map from K1K, which is K star to this. So already we know phi star maps K1 star injectively into the units of A mod x. So phi star map is by the previous lemma. So A mod x star has to be K star. So it is surjective, it is injective, so it has to be. So this proves, so this is where only K theory is required in the proof, that if you have the first K group to be trivial, then A mod xa has trivial units. Any questions till now? Okay. If not, nothing in the chat also. Now, 8 implies 9. So let's again go back, because most of you will have forgotten what is 8 and what is 9. 8 says A is geometrically factorial, dk is A, and A mod x star is K star. Now I have to show that f is a variable. Okay. So as before, we assume, remember, hypothesis includes dk is A. So we are good enough to use our proposition 7, which says that you can take fzt to be of this form. And again, we divide into two cases as we have done earlier and argue analogously. If A1z is 0, then A mod x is kyzt mod A0z. Now you know A mod x star is K star. So you cannot have A naught z to be in K. So A naught z is irreducible when you tensor it with K bar, since it is geometrical factorial. So it is linear. So f is a variable. Main thing, if we have to show it is a linear in Z, which we have already done in the previous case. And being linear in Z is good enough to say that f is a variable. And if A1z is not 0, then as before again, A mod x is kz1 by A1zy. Now you see A mod x star is K star. So A1z has to be a unit, because otherwise the ring A mod x will have non-trivial units. And what is if A1z is a unit? Look at fzt. A1z is the coefficient of t, the leading term, coefficient of the leading term contained t. If it is a unit, fzt becomes a linear polynomial in t or a monic polynomial. You can reduce fzt. So again, f becomes a variable. So this is again easy. Now, here we will use that Russell-Sartre theorem that pi remains a prime and only this thing. 9 implies 1. Again, I go back, and this will complete the first loop, I think. 9 says if f is a line and dk is A, then kxyzt is kxt2. So, okay. So without loss of generality, let's assume we know that fz is, say we can set fzt to be z. Let's take d to be, we define now, we have to use that theorem. So in that theorem, if you remember, there were two domains. R was contained in D. There was an element pi, which was prime in R as well as prime in D, and like that. So our D and R will be like this. So we will take D to be kxyzt. R is kxgt. Obviously, R is contained in D. And our prime element pi is x. If you invert x, it is, one can check that is Rx inverse Z. And d mod x d will be Rx mod R1. Now you apply that theorem, that then d will be R1, and hence kxyzt is kxt2. 6, okay, this completes the first loop. Now 6 and 10. Let's look at 6 and 10, equivalence of 6 and 10. So I have proved that 1, 2, 4, 5, 7, 8, 9, and 1 are equivalent. And also 1, 3, 6. So what I need to do, 6 10 and 9. This implication we have. I will show that 6 and 10 are same, and 10 and 9 will be proved. So let's look at 6 and 10. 6 is A is an A2 fibration over Kx and dk is A, and kzt mod f is K1 and dk is A. So you can forget dk is A, that is the common thing. Now, lemma 2 says A2 fibration if and only if f is a line. In the previous page I wrote, lemma 2 states that for such an A, if A is an A2 fibration over Kx, if and only if f is a line. So you can see 6 and 10 are equivalent. And remaining, we need 10 and 9. That if it is a line and dk is A, then f is a variable. That remains to show. And 10 implies 9. This is by proposition 7. Because dk is A, obviously you remember a part of the proposition 7 said that if f is a line, f is a variable. So you see how much proposition 7 is used in mainly the part of the proof, apart from the results of K theory. Anyways, now, so we are done with the proof. I know maybe I was not good enough to present it, maybe you got confused, but do ask me even later if you have any questions. I can explain the steps. Well, so this proof was entirely for m greater than 1. So what happens when we have m equal to 1? So I have noted several implications will be true even. So the ones which were mostly obvious, the ones I wrote which were obvious will be true even when m equal to 1. But what will not go through is these implications. That A geometrically factorial over K, dk is A, K1A is K star, will not imply that kzt mod f1. See, you cannot apply proposition 7 if you have m equal to 1. Proposition 7 plays a very big role. Every time we are saying either A is linear in Z, or we can reduce it to that A mod X, X inverse is a certain form. So those things will not be there. So 9, so this 9 and 10, 7 implies 9, 7 implies these things will not be there. I think this should be 8. One is 7, one is 8. Yeah. Now, but what Neena Gupta also proved that if xyzt is of this form, xy minus fxzt, where even if you take, probably if you want f0zt to be a non-trivial line, you can take that. But this theorem, this result does not require that. Then Dachshund dk of A is A and MLA is, sorry, this is wrong. This is a typo. MLA is K. It is not A. MLA is K. Now, so this is I have kept this part in slide. This is a modified version of the previous theorem. If someone is not comfortable with K theory, one can go around it and prove a little bit weaker statement. So you see there's geometric factoriality and K1 and A mod X star, K star, those things have not come, but this can be proved. I will not go through the proof of this now. You can have a look later. Now let's come to the part where we show that A is stably a polynomial. There is a typo here also. Okay. Here m is greater or equal to 1. We want to prove that, and we know that f is a line in kzt. Kzt mod f is K1. So we shall need a lemma for this, which will use the fact that kzt mod f is K1. And this is crucial for the construction. Actually, what Neena Gupta had done, she has explicitly given a set of generators for K4. So we will directly show in what coordinate system we can write A1 to be K4. That AW is some polynomials F1, F2, F3, F4. And we will show exact set theoretic equality. So let K be a field, D is an affine K domain, capital Fx is in Dx, and F0 is F0. Suppose D mod F is K1. Then if you go dx mod x to the power m comma f, this ideal, it is a polynomial ring over kx mod x to the power. And how will we apply this? We will take D to be kzt. You can guess. Our fxzt now will be this capital Fx here. Small f is the usual small f. And you know kzt mod f is K1. So in our case, I can write this kzt and fx to be this fx. Yes, this is what I meant. So proof. From the proof of, well, let's see. Let's look at this diagram. Take U to be an indeterminate over Kx and small y the image of y in A. And so obviously capital A is Kxzty. We have a diagram. You have psi is the canonical surjection Kxu to Kxu mod x to the power m. Phi is the surjection obtained by the previous lemma. And so image, and one can check that through the proof of that lemma, x goes to the image of x here, basically. So psi of x and phi of x are same. Kernel phi is x to the power m, comma f. Now, since we have this diagram and these are surjections, we can choose an h in xzt as well as some pq in kxu such that these are, you will see why this choosing of pq and h are necessary, such that see, psi of u is an element in kxu mod x to the power m. Phi is surjective. So there has to be some h in kxzt such that phi of h is psi of u. Similarly, if you take some pxu, and so there is a phi of z goes here. Phi of z goes to kxu mod x to the power m. Now psi is again on. So there has to be some p in upwards in kxu such that psi of pxu is phi z, and similarly for t, phi of t is psi of qx. Now take w to be another indeterminate over A and set w1 to be x to the power m w plus h. z1 is z minus pxw1 by x to the power m. t1 is t minus qxw1 by x to the power. And a priori it is not that obvious why, if I why I'm dividing by x to the power n. Suddenly I'm taking sort of a modification one can say is doing. But we will show that AW is kxz1 t1 w1, which I name as b. So let's see, these are just computations. What is small y? Small y is fxzt by x to the power n by the relation of the ring A. Now just substitute x instead of z. Z is from the first equation x to the power m z1 plus pxw1, and similarly t is x to the power m t1 plus qxw. Now if you break it up, you can make the first terms to be something by x to the, that is f of x pxw1 qxw1 by x to the power m. Now x to the power m will come in the numerator in all other terms. So I can write this plus some alpha times this. X to the power m is only occurring here in the denominator. Similarly for w also, you can do a change by using that equation where you have w is w1 minus h of this thing by x to the power m plus some beta, where alpha, beta are in B. They are polynomials in Z1, T1, W1, and X. They are in B. Now, what about these first terms? Now, you know, psi of fx, px, q, x of u is what? By our choices, this is phi of fxz, but kernel of phi had fxz. So this is 0. So instead of u, if you substitute w1, u was an indeterminate. You will have fx, px, w1, and this is contained in x to the power m kx. So it's like u is like w1 here. So it's contained in x to the power of this, which is contained in x to the power. So y belongs to b. See, y had this thing as the first term. We needed to justify why upon dividing by x to the power m, still it remained. That is taken care of by the choices of h, p, and q. And similarly, for psi also, you can show that w is contained in B. Now z is already in B because z is like this and t is like this. So AW is a subset of. Now we have to show the other way. Enough to show that B is contained in A. Again, start with, now we will deal with Z1 and T1. Z1, we write this. This is something by x to the power m plus some gamma, where gamma is in AW. And T1 is also, you can write as some this thing by x to the power m plus delta, where delta is in AW. And again, we use the fact phi of z minus pxh and phi of t minus qxh are both 0. So they are contained in kernel phi. So they will be of the form ax to the power m plus bf, cx to the power m plus df. And y is what? Y is fxzt by x to the power m. So always you have this w1 z1 t1 to be in it. Okay. So b will be contained in AW and hence b is kx3. Okay, so this is, I think, completes that A is stably a polynomial. Any questions again? Otherwise, I will make a remark on a short result. So it was mentioned in lemma 6 that Macaulay-Limonov invariant of our A was contained in Kx and Kxzt was contained in dk. In fact, we have this actual lemma that if f is a non-trivial line and m is greater or equal to 2, dk of A is Kxzt and MLA is Kx. Recall if m was equal to 1, irrespective of the fact whether f is a line or not, we will have that dk is the whole ring and ML is just k. So this actually creates an obstruction for A to be a polynomial ring if f is a non-trivial line. So you already know what, how to, let's try to prove this, or I will give just a sketch of proof. So by proposition 7, we know that dka is not equal to A. Because why? Because f is, by our hypothesis says that f is a non-trivial line. What was proposition 7? If dk is a, then f cannot be a non-trivial line. That is, if kzt mod f is k1, f has to be a variable. So by proposition 7, we can directly say dk is not A. But you know, kxz is contained in dk. So what you should have? You must have equality. Otherwise, it is not possible. This subalgebra is contained in dk, and dk cannot be the whole thing. So you cannot have y in it. So dk is just this. Now to prove that MLA is kx. So what we have to show? That every non-trivial exponential map will have x in its ring of invariants. So let phi belong to expa is non-trivial. Transcendence degree of a phi is 2 because it is 3 minus 1. And since it is 2, you can have two algebraically independent elements, algebraically independent over k, which are in ring of invariants of some exponential map that is in dk, and which is equal to kxzt. So you can write alpha and beta in this form. Alpha is x times alpha 1 plus some alpha 0. Beta is x times beta 1 plus some beta 0. And alpha 0, alpha 0 is a polynomial in just zt, and alpha 1 and beta 1 are polynomials in x, z. Now, suppose the first terms without x, alpha 0 and beta 0, are algebraically independent over k. You can consider a proper admissive z filtration, which is stated in lemma 3 and the induced graded ring. What we achieve from this is, on the GR, on this ring B, there will be an induced non-trivial homogeneous map such that the images of alpha 0, the alpha 0 bar and beta 0 bar will be contained in the ring of invariants. Now remember, what was alpha 0 and beta 0? They were polynomials in Z and T. Now you also know that Z bar and T bar are algebraically independent over K in B. And so this alpha 0 bar and beta 0 bar are also algebraically independent over K. Because if there is a relation, they will imply relations between Z bar and T. And B phi bar is also algebraically closed in B. So K Z bar T bar is contained in B phi bar. Now, there is a strange fact, or the interesting thing. What was the relation in B? Relation in B was x to the power my is f of zt, not capital F, f of small zt. That is again deduced in lemma 3. But if you accept this, you see z bar and t bar are already in the ring of invariants. So x to the x bar to the power m into y bar is again in the ring of invariants, but it is factorially closed. So it will force both x bar and y bar to be in the ring of invariants. So what does this tell? This map becomes trivial. It kills everything. So phi bar cannot be a non-trivial. And this gives the contradiction. So alpha 0 and beta 0 are algebraically dependent over here. So you can say there is a polynomial in two variables. If I plug in alpha 0 and beta 0, h of that thing will be equals to 0. And now see, look at the equations. So alpha minus x, so you can take some combination of alpha 0 and beta 0 and make h of alpha beta so that it's a multiple of x, because it is x into something plus alpha 0, x into something plus beta 0. So h of alpha beta you can assume to be in xa, and hence by factorial closeness of a phi you will have, since alpha beta are only both in a phi. So h of alpha beta is, if it is in xa, x will belongs to a phi. So Makalle-Lemon of invariant is x, because x is always there. Few concluding remarks or ending remarks, I will say. If a is this and m is greater than 1 and f of 0 z is a line, then it follows from the theorem stated that either you have dka is a and respectively mla is k, or dka is kxzt or mla is kx, according as whether a is kx2 or a is not kx2. And see, if I a is kx2 will happen if and only if a is k3, and a is not kx2 is if and only if a is not isomorphic to a polynomial ring in 3 variables. So whether the line is trivial or non-trivial, that creates the difference. However, if m is equal to 1, the Dodson and the Makalle-Lemon of invariants are always trivial. And this is easy. Well, if you go to lemma 6, just interchange the roles of x and y. Here x was special. We will always take like the x being fixed by the exponential map, but I can always change the roles of x and y because both the powers are 1. So Makalle-Lemon of invariant will be trivial. So this question whether a is isomorphic to k3 remains open for m equal to 1 and f0t, I will say, is a non-trivial line. I should add this word, a non-trivial line in kz. So with this, what I plan to say today is almost over. But if you have any questions or any proofs you think I should go and revisit. Maybe proof of proposition 7. Okay. Any questions till now? I can't see the chat also.
So
Yes.
let me try to summarize. To provide a counterexample for the Zariski cancellation problem, what we do, we take a field of positive characteristic.
Exactly.
Then we take kzt and a polynomial, which is a non-trivial line, which means that
Yes.
it defines a curve which is isomorphic to a affine line, and it cannot be translated into coordinate axis by an automorphism, right?
Exactly.
And could you please provide an explicit example of such?
Yeah. I'm actually scrolling for that so that you have an idea of how to.
I guess I remember.
Here. Okay. So I will state this. You can take this f. Take any s and s such that these conditions are satisfied. S greater than 2 and p should not divide s. All of these will be non-trivial lines.
Okay, and after I have such f small f, I take a threefold in four-dimensional space given by x to the mth power, where m is greater than 2, multiplied by y minus f
of some xzt such that this is the 0th. This is the first term of that.
Substitute x equal
that means
to 0.
If you the first term of the polynomial.
Yes, I see. Thank you.
Yeah, that is what. Okay, what shall I do now? Shall I go through the proofs of all the propositions, or if you want to discuss something? Maybe let's do proposition 7, because Or maybe I will go through each of the proofs quickly so that if you look at the slides, you have an idea of what to look for. It should be done by me once. So let me see which are important things. Lemma 1, Lemma 2, I'm skipping. These are just commutative algebra. You can follow. It's not that big deal. Well, Lemma 3 is just this. So this is another thing which one can do. What is the associated graded ring? So if A is our that usual A, you can get a proper admissible Z filtration such that under that filtration, GRA will be isomorphic to this, x to the power my minus fz. So whenever I was referring to B as GR of A, I meant this ring. So this can be proven. So I'm not going to this. This is another very interesting proposition and it's a major step. So now see, we have B, obtained B now. And if you remember by the theorem of Dukson, Hadas and Makallibanov, we were always using that if you have a proper admissible Z filtration, a non-trivial exponential map goes to a non-trivial homogeneous exponential map, GR. So we need to study this ring B. So what are the properties of what are the possible exponential maps on this B? So if you consider this as a graded subring of kxx inverse zt, where bi is this thing. Now suppose there is a non-trivial homogeneous exponential map phi on this graded ring, which kills y, or I should say which keeps y invariant, such that ky is in b phi. Then there exists w in b phi such that kzt is kw. So you can see, you can pick two algebraically independent elements, provided y is there. Y is very special. It's not just because m is greater or equal to y is special. That y and w both will be in b phi and kzt will be kw1. In fact, what should be, this is a threefold again. So the ring of invariants will be a two-dimensional. And actually, the b phi will be equal to this. So this is digit. So if y is there, then you can have w. And this is another result, which is quite maybe you can say of a different flavor. This is of a very simple Z, that it is just a polynomial in Z. This was already proved by Makallibanov for characteristic 0, and Neena Gupta proved it even in positive characteristic where degree Z is 1. The D is kxyz mod x to the power my minus pz. Now, it says that there does not exist any exponential map on y such that y is in D phi. So keep also that in mind. Now, this was lemma 6. Well, lemma 6 gives two examples of exponential. Why did I say that kxz is contained in dka and mla is contained in kx? Because I will construct two maps, phi 1 like this and phi 2 like this. You will see in ring of invariants of phi 1 and ring of invariants of phi 2 will already make kxz. So that has to be contained in dk of a. And the intersection is kx. So Makallibanov, so kx will be there. Well, this is one lemma, but let's skip this. So proposition 7, let's look at a proof of this. Now, suppose you have this situation, and that means we have dka is a. So what I can say, dka is not equal to kxzt. So there must be some non-trivial exponential map, the ring of invariants of which is not contained in kxzt. Because otherwise dka will be, it's not contained in kxzt. So consider A as a subring of kxx inverse zt, and you define a filtration like this. And the GRA will be this thing. Fzt is f of 0zt. By this theorem of Dukson, Hadas, Makallibanov, that phi now will induce a non-trivial homogeneous exponential map on the GR such that rho of a phi is contained in GRA of phi. Now, what we will do is a little bit computational and also given in the previous lemmas. If you take some G, look at the term inside the bracket first. If you take something in G is in A phi, which is not in kxzt, and you take rho of this, it will look like some Gij of z bar t bar, x bar to the power I, y bar to the power j, where due to the relation, the power of x can vary only between 0 and strictly less than m, because as soon as you have x bar to the power m, you switch it. You write it at fzt by 1. And j is positive. See, it has to involve a positive power of y, because g I have taken outside kz. So if you have something like this, and using the factorial closeness, this is the highest, like the highest homogeneous term of g bar. So this is in b5 bar. So what will you have? Y by factorial closeness of b5 bar, you will have y bar in b5. Now you apply that proposition 4, which said if y was in b, this b, then I will have some w such that kzt is kyw like that. So you will have that z1 in this, kz1 t1 is kz1 bar and z1 bar in b5 bar. Then if you take the pre-image, obviously kzt will be z1 t1. So this is how you come across that z1 t1 coordinate system, by going to the associated graded ring and getting the coordinate system there. Now, let h of z1 t1, I'm just writing this f of zt is also as a polynomial in z1 t1. Summation ai z1 t1 to the power I. K tilde is the algebraic closure of K. Phi bar induces, now phi bar will also induce a non-trivial exponential map if you tensor with the algebraic closure. Why? Because this is just you are increasing your ring of coefficients. So in this algebraic closed field, how will this look like? We will use this fact. We will use one fact that there exists infinitely many beta in K bar such that Z1 minus beta is prime in B tilde. Well, what is needed to use this? You need an infinite field to have a choice of infinitely many beta. But a priori, we are working with, you might work with finite fields of positive characteristic. So the field may not be finite a priori. So that's why we move on to the algebraic closure. Algebraic closure, you know, of any field is always infinite. So you will have sufficient choices of beta, and you can choose such that if you go modulo Z1 bar minus beta, and this leading coefficient an of this is non-zero, 5 bar will induce a non-trivial exponential map phi tilde. And this is how you can write in that field. The main thing to observe is, now if you go Z mod beta, it is a polynomial in x, y, and t1 only. And I will go to this result again. You use lemma 5. What does this lemma 5? If z degree of pz is more than 1, y cannot be in the ring of invariance of an exponential. So in that case, if the z is like t1 in that case. So if the t1 degree is more than 1, y will not be in the ring of invariance of phi tilde. And we will show y is in the ring of invariance of phi tilde. So what will we have? That it is linear polynomial in t1 and hence a variant. That's how the proof will go. So let's finish that part off. So by lemma 5, we will have n equal to 1 in this case. And we have proved that we have proved the first part. So if n equals to 1, fzt is like a0z plus a1z t1. That was first part. Now if a1 is 0, it is a linear polynomial in Z, and you can finish off the remaining. That is not that much great. Anyway, so proposition 7 was a key proposition in the lemma, and for that we needed the previous results also. So all of these results are linked. Any more questions or doubts?
Okay, Nikhilesh, in the last minutes, I was interrupted by the phone call. So
sorry,
did you,
sir. Yes.
Did you finish? So this is all what you wanted to tell?
Yes, yes, sir. I think I will share the slides with the group, and everything is there in the slides. And maybe the presenting proofs in this format might not have been that much. I was not that comfortable, or maybe due to lack of technologies, we are behind. But we can discuss also later on if someone has any difficulty with any step of the proofs.
Thank you very much. It's clear that the result is very deep and technically difficult, but at least we were able to follow the scheme.
Yes, I think Kirill pointed out quite nicely, and then in a format that we take a non-trivial line and we do x to the power my minus something such that if you plug in x equal to 0, it becomes that line, and that will give you the counterexample. That's how we construct. And this is a way of constructing many counterexamples like this, probably. But the m equal to 1 case remains open, sir. That case, this methods might not be, I do not know what happens. And sir, I will also want to add, we have Neena Gupta in the audience, our PI from the Russian side. If she wants, she can put in some comments, like if I have many mistakes or not. Neenadi, are you there?
Yes, I am here, but Nikhilesh, you have done a very good job. I myself would not have been able to present it so well.
No, your paper was there to help me out always.
Very well done. Yeah.
Okay, so maybe some other questions, comments from Russian side, from Indian side, dear colleagues, please. If not, then thank you very much. We are definitely impressed. So we need to think more and maybe to read once more time your presentation. Yes. And try to understand all details, yeah, because it's an important technique. Do you believe that this technique can be applied to other problems? So that you may have some development, right?
Well, I think so, because it gives proofs which are free of characteristics. Many problems which are proved in characteristic 0 might be like interesting if you want to investigate in positive characteristic, and there some results might go through and some might not. But we have the technique of exponential maps, which are almost like local and nilpotent derivations. So some things go that needs to be investigated. Even I will say all the results of LNDs, are they true for exponential maps? Just the properties of LNDs, one can take up a project like that and investigate.
I see.